Copper ore deposits. Copper ore deposits are geological formations containing significant amounts of copper-bearing minerals. These deposits are formed through various geological processes and are mined for the extraction of copper metal. There are several types of copper ore deposits, each with distinct characteristics and formation processes. Here are the main types. Porphyry copper deposits. Characteristics: large, low to medium-grade deposits. They contain disseminated copper minerals and are usually associated with large volumes of rock called porphyry. Formation: formed from hydrothermal fluids that originate from a magma chamber deep in the Earth's crust. These fluids ascend and precipitate copper and other minerals as they cool. Examples: Chuquicamata in Chile, Bingham Canyon in the USA. Sediment-hosted stratiform copper deposits. Characteristics: these deposits are found in sedimentary rocks and are typically high-grade. Formation: formed from copper-bearing fluids that migrate through sediments and precipitate copper minerals in porous rocks or chemical traps. Examples: Central African Copperbelt, Redstone Copperbelt in Canada. Volcanogenic massive sulfide deposits. Characteristics: formed at volcanic mid-ocean ridges and back-arc basins. They contain copper along with other base metals like zinc and lead. Formation: formed from hydrothermal fluids expelled from volcanic activity, which precipitates sulfide minerals as they come into contact with cold seawater. Examples: Kidd Creek in Canada, Flin Flon in Canada. Skarn deposits. Characteristics: found at the contact zone between igneous intrusions and carbonate sedimentary rocks. They are rich in copper and other minerals like iron, tungsten, and gold. Formation: formed by the chemical reactions between hydrothermal fluids from an igneous intrusion and the surrounding carbonate rocks. Examples: Erzberg in Indonesia, Antamina in Peru. Supergene enrichment deposits. Characteristics: these deposits are secondary enrichments formed near the Earth's surface. They contain high-grade secondary copper minerals. Formation: formed from the weathering of primary copper deposits, where copper is leached and reprecipitated at a lower depth. Examples: Morenci in the USA, La Escondida in Chile. Sediment-hosted copper deposits. Characteristics: typically found in red bed sequences, often associated with evaporites. Formation: copper is deposited from saline, oxidized waters in reducing environments. Examples: Zambian Copperbelt, Zhezkazgan in Kazakhstan. Carbonate-hosted copper deposits. Characteristics: occur in carbonate rocks such as limestones and dolostones, often with associated silver and zinc. Formation: formed by the replacement of carbonate minerals by copper minerals due to hydrothermal activity. Examples: Tsumeb in Namibia, Kipushi in the Democratic Republic of Congo. Copper ore deposits are critical resources for the production of copper, which is essential for electrical wiring, plumbing, and numerous industrial applications. The extraction and processing of copper from these deposits involve mining, crushing, grinding, flotation, smelting, and refining. Formation of copper ore deposits. The formation of copper ore deposits involves various geological processes that concentrate copper minerals into economically viable quantities. Here are the primary processes and conditions under which different types of copper deposits form. 1. Porphyry copper deposits. Formation process. Magma generation. Deep in the Earth's crust, magma forms and begins to rise towards the surface. Hydrothermal fluids. As the magma cools, it releases hydrothermal fluids rich in copper and other metals. Crystallization and precipitation. These fluids ascend through fractures and porous rocks, cooling and precipitating copper minerals such as chalcopyrite, bornite, and molybdenite within the host rock. Alteration zones. The deposit forms alteration zones with different mineral assemblages, such as potassic, phyllic, argillic, and propylitic zones, each indicating varying conditions of temperature and pressure. Example: Chuquicamata in Chile, Bingham Canyon in the USA. 2. Sediment-hosted stratiform copper deposits. Formation process. Sediment deposition. Copper-bearing fluids migrate through sedimentary basins and are trapped in porous sediments. Chemical precipitation. Copper minerals precipitate from these fluids in reducing environments, often in association with organic matter or sulfide minerals. Stratification. The minerals are typically layered or stratiform, following the bedding planes of the sedimentary host rocks. Example: Central African Copperbelt. 3. Volcanogenic massive sulfide (VMS) deposits. Formation process. Volcanic activity. At mid-ocean ridges or back-arc basins, volcanic activity causes hydrothermal vents to expel mineral-rich fluids. Seawater interaction. These hot fluids mix with cold seawater, causing rapid cooling and precipitation of copper, zinc, lead, and other minerals as sulfides. Layered deposits. The minerals form massive sulfide layers on or near the seafloor. Example: Kidd Creek in Canada, Flin Flon in Canada. 4. Skarn deposits. Formation process. Intrusion of magma. An igneous intrusion comes into contact with carbonate rocks, like limestone or dolostone. Metasomatism. The heat and fluids from the magma cause chemical reactions with the carbonate rocks, forming new minerals, including copper-bearing minerals. Zoning. Skarn deposits often show zonation with different minerals forming at varying distances from the intrusion. Example: Erzberg in Indonesia, Antamina in Peru. 5. Supergene enrichment deposits. Formation process. Weathering. Near-surface primary copper deposits undergo weathering, causing the copper minerals to oxidize. Leaching and transport. Copper is leached from the oxidized zone and transported downward by acidic groundwater. Reprecipitation. Copper reprecipitates at a lower depth in a secondary enrichment zone, often forming high-grade secondary minerals like chalcocite. Example: Morenci in the USA, La Escondida in Chile. 6. Sediment-hosted copper deposits. Formation process. Saline waters. Oxidized, copper-bearing saline waters migrate through sediments. Reductive traps. Copper precipitates in reducing environments created by organic matter or other reducing agents in the sediments. Formation. Often found in red beds and associated with evaporites. Example: Zambian Copperbelt. 7. Carbonate-hosted copper deposits. Formation process. Hydrothermal fluids. Hydrothermal fluids interact with carbonate rocks. Replacement. Copper minerals replace the carbonate minerals in the host rock. Complex mineralization. These deposits can be complex, with copper often found alongside other metals like zinc and silver. Example: Tsumeb in Namibia, Kipushi in the Democratic Republic of Congo. These processes result in various types of copper ore deposits, each with unique geological settings and mineral compositions. Understanding these processes is crucial for mineral exploration and the efficient extraction of copper. Properties of copper ore deposits. Copper ore deposits exhibit a range of properties depending on their type, formation process, and mineral composition. Here are some key properties of copper ore deposits. 1. Mineralogy. Primary minerals. Common primary copper minerals include chalcopyrite, bornite, chalcocite, and covellite. Secondary minerals. These include malachite, azurite, cuprite, and tenorite, often formed through weathering and oxidation processes. 2. Geological setting. Host rocks. Copper deposits can be found in a variety of host rocks, including igneous, sedimentary, and metamorphic rocks. For instance, porphyry deposits are typically associated with intrusive igneous rocks, while sediment-hosted deposits are found in sedimentary basins. Structural controls. The presence of faults, fractures, and breccias can influence the formation and localization of copper ore deposits. These structures provide pathways for mineralizing fluids. 3. Ore grade. Concentration, the copper content, or grade, can vary widely. Porphyry copper deposits typically have low to medium grades, whereas supergene enrichment zones can have much higher grades. Economic viability, the profitability of mining a copper deposit depends on the ore grade, volume of the deposit, and accessibility. 4. Texture and structure. Dissemination. In porphyry deposits, copper minerals are often finely disseminated throughout the host rock. Massive sulfides. In VMS deposits, copper minerals can occur as massive sulfide layers or lenses. Veins and stockworks. In skarn and some sediment-hosted deposits, copper minerals may be concentrated in veins or stockwork zones. 5. Geochemical characteristics. Elemental associations. Copper ore deposits often contain other valuable elements such as gold, silver, molybdenum, zinc, and lead. For example, porphyry copper deposits commonly have associated molybdenum and gold. Alteration zones. The presence of hydrothermal alteration minerals like cerussite, chlorite, and epidote can indicate proximity to copper mineralization. 6. Physical properties. Density and hardness. Copper minerals typically have high densities and variable hardness. For example, chalcopyrite has a density of around 4.1 to 4.3 g/cm superscript 3 and a Mohs hardness of 3.5 to 4. Conductivity. Copper minerals are good electrical conductors, which can aid in geophysical exploration methods. 7. Surface characteristics. Oxidation and weathering. Near-surface copper deposits often undergo oxidation and weathering, leading to the formation of secondary copper minerals like malachite and azurite. Supergene enrichment. The weathering process can lead to the formation of high-grade supergene enrichment zones beneath the oxidized cap. 8. Economic and environmental factors. Extraction methods. The properties of the deposit influence the mining method used, open pit, underground, or in situ leaching, and the processing techniques required to extract the copper. Environmental impact. The type of deposit and its location can impact the environmental management practices needed to mitigate the effects of mining activities. 9. Spatial distribution. Deposit size and shape. The size and shape of copper deposits can vary significantly. Porphyry deposits are typically large and disseminated, while VMS deposits can be relatively small but high-grade. Geographic location. Copper deposits are found worldwide, with significant concentrations in regions like the Andes, Chile, Peru, the southwestern United States, the Central African Copperbelt, and parts of Australia and Canada. Understanding these properties is crucial for effective exploration, extraction, and processing of copper ore deposits, ensuring that mining operations are economically viable and environmentally responsible.